All right, welcome back, everyone. So today we're going to kind of shift gears a little bit and start talking about the particle model of matter. So let me just kind of briefly summarize what our plan is for the next couple of weeks. So, we've been talking about energy all this time. And we've been focusing on mechanical energy, things like kinetic and potential energy. So our goal is now to use these concepts in order to understand internal energies in terms of these mechanical energies. So in other words, in the beginning of the course, we just said, okay, there's this concept of thermal energy. We can go to a lab, take a glass of water, heat it up, figure out how much energy did we put in order to have some temperature change. The same with phase transitions. We can melt a piece of ice, figure out how much energy it took, get some numbers, and that was enough. So in order for us to be able to figure those interactions out, we didn't need to know anything about the matter itself. So those things were done by scientists before they knew that matter was made out of atoms. So, but what our goal will be now is actually look at the atomic behavior inside materials in terms of their mechanical energy, so the motions of individuals, atoms, or molecules, and their interactions described by potential energy. And by looking at those at that microscopic behavior, microscopic just means very small and atomic level, to go back and try to explain that macroscopic behavior of thermal and bond energy. So that's kind of the goal for the next couple of weeks. Okay, so we'll start by thinking about, and you'll do this in DL2, by the atomic hypothesis. And here's a physicist, Richard Feynman, who has a Nobel Prize in physics. So he once said that, I believe it's the atomic hypothesis that all things are made out of atoms, little particles that move around in perpetual motion, attracting each other when they're a little distance apart, but repelling each other when they're being squeezed into another. So what he believes that if all scientific information were to be lost, this would be the most valuable idea to be passed on to future generations. So although this kind of seems like a rather simple statement, it actually has a lot of profound implications on how we view and understand the world right now. So let's kind of think about this. Well, the fact that all things are made out of atom was definitely not something, it's common knowledge now, but that's not something that was known for many years, even after people started doing science and trying to figure out how the world works. The fact that atoms attract each other when they're somewhat close together is also really important, because if this attractive force didn't exist, then we wouldn't exist. Then we would just have a bunch of particles, subatomic particles floating around in a big soup of the universe, and there would be no stars and planets and people and so on. But then there's also a force that repels these particles when they get really close together. So if that force didn't exist, then everything, all that matter would just collapse to kind of one point, and again, we wouldn't exist. So these are kind of really important ideas. And what we're going to do next is going to look at this this interaction of atoms and try to describe it with a potential energy. Okay. So again, as I sort of already briefly summarized, our goal here is to understand macroscopic phenomena. Macroscopic just means something that, is on our scale, something that you can see and touch and pick up, like, a whole glass of water rather than just a couple of atoms within that water. So that microscopic phenomena we looked at the start of the quarter: melting, vaporizing, idea of temperature and heat capacity in terms of the microscopic constituents and its behavior. So in terms of atoms and molecules. So what we're going to start with is just thinking about two independent particles. So they could be atoms, they could be molecules, but the idea here is that they're neutral. So there's no, they're neutrally charged. So the forces involved will not be electrostatic, but just between these neutral atoms. And what we're going to model these two atoms as if they're attached by a spring. So that, again, that spring mass that we spend so much time focusing on, you would think, okay, that's kind of a really specific thing. Why we're focusing so much on it? Well, because that simple of idea of this harmonic oscillatory motion is actually used to explain a lot of behavior, including interaction of atoms on an atomic scale. So of course, there's not a real physical spring that's holding them together, but we can use these concepts of springs to explain the various forces that are seen in nature when these atoms interact. So you're going to actually, in DL, start with kind of a typical spring and modify in order to fit the realistic behavior of interaction between atoms, and you will end up with something like this. So this is what is known as sometimes we call it the pairwise potential, because it describes interaction between pairs of particles. I use the word particles just to be more general, because it could be atoms, it could be molecules, but sometimes I'll go between these different words. More specifically, it's known as the Lennard-Jones potential, after scientists who kind of came up with this. All right, so we're gonna basically I'll spend the remainder of this recording really dissecting and trying to understand what this plot is telling us. So what are we plotting here? It's potential energy, but it's no longer in units of joules, but it's in units of this constant, which we call the potential well depth, and we use the Greek letter epsilon to describe it. So I'll get to that shortly. And then, so it's some kind of scale unit of energy as a function of separation. So this R, which I introduced briefly in the previous recording, this idea of looking at potential energy as a function of the distance between two things that are interacting. So it's that separation R. That R is measured from the centers of our particles. And this doesn't have, R is a distance, so it should really have units of things like meters. But it has, instead, we're doing it in units of atomic diameter. So for example, a separation of 1, what that means is the distance between the two atoms is 1 diameter. How could that be? It's when they're exactly touching. So if they're touching and we're measuring from the center, that's 1 radius. That's 1 radius, which equals a diameter. So this separation is when they're touching. Anything below 1, you're kind of squeezing them together. All right. So there's a couple of special locations here. So like with a regular spring mass, there's an equilibrium distance. So if you, on a macroscopic level, attach 2 balls with a spring, there's going to be a natural separation when there's no forces acting on it that system will have, which we call equilibrium, the same way we did for hanging spring mass. So we call this equilibrium separation R naught. It's just the letter that we use to describe it. And it happens to be for all these particles which interact with this potential to be equals to exactly 1.12 of sigma. And sigma, remember, is atomic diameter. So it's actually really, really close. So they're not quite touching at their equilibrium separation, but they're very close. So it's 1 diameter plus like 1/10 of a diameter apart. So they're really close, but not exactly touching. So this is going to be a very important separation that we will discuss. Okay, and then the bottom, so the energy, the lowest potential energy at the equilibrium, because remember, at equilibrium is when what potential energy is the lowest. There's no forces here, the slope is 0, and it's the minimum potential energy is at minus epsilon. So the well depth itself is known as, we call it well depth because it's that minimum potential energy, and it happens to be, exactly, it's scaled to be -1 unit of epsilon. So the reason why we use these strange units instead of doing directly joules and meters, let's say, is we want this potential energy to generalize to all atoms. If you want to specifically draw this for 2 nitrogen atoms versus 2 gold atoms, then the 2 plots would look different because they will most likely have different well depths and different diameters. But this describes any general pair of these interacting atoms or even molecules. Okay, so this is some of the kind of important units and vocabulary around this potential. And I want you to now try to remember some of the ideas of connecting potential energy and forces to answer a couple of questions here. So atoms at a large distances, so at r, well, this is large on this atomic scale, so at a distance bigger than about 3 diameters, so out here, do not interact. So is that true, false, or there's just not enough information? So think about, again, go back to these ideas of force and potential energy. Interact, what does the word interact mean? Do they feel a force? So the answer is true. Why is that? Well, if you look up here, the plot basically becomes constant. So it's not the fact that the potential energy goes to 0. That's not what makes them not interact, but the fact that it becomes constant. And when it's constant, what is the slope? Force is related to slope. The slope here is practically 0. I mean, they're still interacting here, and it just gets weaker and weaker and weaker and weaker. And by about 3 and greater, it's so weak that we can pretty much, so it's true within an approximation. So as these particles get farther apart, that interaction gets really, really weak until we can basically say that they're no longer interacting and the force is 0. So because the slope goes to 0, so does the force. Okay, another question. It is practically impossible to squash one atom completely into the other one. So think again about forces here. And again, this is true. So why is that? So first of all, when are you squashing them together? Remember, this is when they're touching at 1, and anything below 1, it kind of goes a little bit like less than 1 here. Do you see how the slope becomes practically, the potential energy plot becomes practically vertical? What's the slope of a vertical line? It's basically infinity. It's not quite infinity, but it's really, really, really large. So a really, really large slope implies a huge force, which means that it would take a lot of force, a lot of energy to bring these particles, anywhere less than 1. So you're kind of squeezing them together. So this really represents that really large force. Okay, so now let's kind of break it down. Let's look at different regions of this potential energy and think about, what are the forces involved here. So as I just discussed with the previous clicker question, right here, the slope is it's practically vertical. So the slope is huge. So I'm kind of representing it by drawing a very long line. Now also the direction matters. The direction is towards the right, because remember our ball is rolling downhill here. That's the direction where potential energy is decreasing. So what does that tell us about the type of force it is? Well, to the right is the direction where the separation between these 2 particles is increasing. So that force wants to bring them apart. So that's why over there it's a repulsive force. So kind of remembering the beginning of this recording when I read out that Feynman statement, what did he say was part of the atomic hypothesis is that there's this repulsive force when atoms are trying to be squeezed together. And that's exactly represented right here by this part of the potential energy. Okay, what about right here? If we look at this location, well, now our ball is rolling this way, again, towards decreasing potential energy. So in this case, the force points to the left. So the slope is positive, that minus sign in the equation makes the force negative. So to the left means towards the direction where the separation between the two particles is decreasing. So that force wants to bring them back together. So that's what makes that, that separation, when those two particles are at that separation, they're feeling an attractive force. So think about these two particles attached by a spring. When you pull them apart, they want to come back to equilibrium. So they want to, the force is attractive. When you squeeze them together, again, they want to come back to equilibrium. The force is repulsive, but it's not exactly the same as the classical spring mass or spring we looked at, because for that one, it kind of didn't matter if you brought them some distance closer together or farther apart, that force was the same, where here the force gets much stronger when you squeeze them together and kind of gets weaker as you pull them apart. So it doesn't quite behave like our classical spring mass, but at least very close to equilibrium, you could see this sort of the same parabola. So very close to equilibrium, it's the same, but then as you move farther apart, when you squeeze them, it gets really strong, and when you pull them apart, it gets weaker and weaker and weaker. Okay, now as you see over here, once we get about over 2 diameters apart, then the force becomes kind of really small, practically negligible as we go 3 or beyond. So it's still an attractive force, but a very small one. Oh, I guess that was it with the slide. So one more thing I want to say, also at equilibrium here, there's no slope there. So the slope goes to 0. So the force is 0. So there's big repulsive force. Then at equilibrium, that's when they're most happy with no force. Over here, it's an attractive force. As they move farther apart, the interaction goes to 0. So, in this recording, I basically summarized the structure and the importance of this Lennard-Jones pairwise potential energy. And in the next couple of recordings, we're going to go kind of into more details and think about how these particles, interacting particles, behave when they also move. So we're going to introduce the idea of kinetic energy and what is the total energy that a pair of particles have? How does that determine the various motions? And we're also going to slowly move into thinking about bonds and when two particles are bound versus not. So this potential energy will help us explain that. So we already kind of saw that when they're farther apart, they're no longer interacting. So if these two particles are found farther apart, we will look at that, or we will define that as if the bond between them has been broken, compared to when they're confined to move within a smaller separation, then they're still bound. So more of this is coming soon. See you next time.